Okay, so in this problem, I don't have a description here, but what we want to do is draw the shear force and bending moment diagram for this. And we talked about in class that the first step would be probably to find the reaction. So let's do that. Now remember, I'm doing shear force and bending moment. So when I assume my reactions here at the left-hand side, I'm going to assume positive shear. Let me go ahead and just call that A and B to give it some values. And on the right-hand side, I'm going to also assume positive shear. Right? Remember our sign convention? It's going to be up on the left-hand side and down on the right-hand side. Both those forces are going to try to create this object to move clockwise, right? So the first step will be to find those reactions. So I'm going to sum moments. It doesn't really matter whether I choose A or B. I'll just choose A. So let's sum moments about A. So the shear at A will create no moment about A, but the two P forces will, and they will be positive or negative with my sign convention. Negative. So I'll have negative P times L, and then negative P times 2L. And then the shear force at B, the way I've drawn it, will also create negative moment. So I have negative the shear at B times 3L. And I don't think it's hard for you to see that the shear at B is going to be equal to minus P. So what does that tell me? The shear force at B is negative P. Right? So then I'll sum forces in the y direction, and I should be able to get my reaction at A. So summing the forces, I have the shear force at A acting up. Let's see, P is down, the next one is down, and the way I've drawn it on my free body diagram, the shear at B is also down. But remember, since I've already solved for that, I'm going to put that negative P value right in there. So if you check that out, you'll see that the shear at A is positive P. So far, so good? That shouldn't be a surprising result. You'll notice that the two forces, the load is symmetric. They're symmetrically spaced, so you would expect the reactions to be equal to P.
Why would it not be negative 3P?
Well, remember, this is a minus P, so you put a minus P in there, the minuses make this positive P. Right? Minus a minus.
Oh, yeah, that's what I said.
And really, you only have 2P acting down. You really can't have more than 2P acting in any other direction. Also, what do we know about A in terms of moment? The moment at x equals 0 is, and what is the moment at x equal 3L? 0. So we know a lot about our shear force and bending moment before we even get started. Okay, what I like to do is to create kind of a template. So I'll redraw the beam, and now I'll put everything in the right order. So I've got my shear force acting up is P, and on this side it's acting up, and it's P, right? And I've got my two loads also P, and they're a distance L apart. So kind of what I like to do is create a little template. So I know I'm going to start on the left side and I'm going to go to the right side. So that's kind of the range of my diagram. So I'll come in here now and I'll establish that I'm working in the positive X direction, and this is going to be my positive shear force. And I like to put a unit there. I know these don't have any units, but let's just use the US unit. So we'll just say that all those shear values will have the units of kips. Now, what do I know about the shear in this problem? Starting at A, what is the shear at A? It's positive P. What is the shear at B?
Or negative P.
Negative P. So if my diagram, which I start at positive P, it better land on negative P. If it doesn't, something's not right. I also know that I've got some interesting points here at P. What happens if I go from the left side to the right side of P? Something's going to change, right? What's going to change? Shear, moment, what? Shear. So that's going to be an important point. So I'm going to add that into my my template as a critical place that I might want to keep track of things. Now, I'm starting at P. I want to know what the value is over here at L. Remember, we have an expression that says the change in shear is equal to the area under the load diagram. What is the area under the load diagram from 0 to L? 0. So it says the change in shear is 0. So that means if it starts at P, it better end at P. We also have the differential relationship that says the slope of the shear diagram is equal to the load. Right? What is the load from 0 to L? 0. What kind of curve has a 0 slope? A horizontal line. So there's my shear diagram for the first section, 0 to L. So far, so good? So what happens now as I go from the left side to the right side and go under this negative force? What happens to my shear there? So I'm at P. I should drop down to 0. What's the change in shear from L to 2L? According to my relationship, it should be the area under the load diagram. What's the area under the load diagram from L to 2L? 0, so there should be no change. It should stay 0. And what's the slope of the curve there? It's given by the load. What's the value for the load? 0. What kind of curve has 0 slope? Horizontal line. So in this particular loading, there is no shear in the middle third of the beam. Then what happens? I go from the left side to the right side. Do I have a change in shear? Yeah, how much? P. Minus P. So if I'm at 0 and I subtract P, I get minus P. What's the change in shear from 2L to L? We'll go up to the load diagram. What's the area in the load diagram? 0. So there should be no change. Hey, look at that. I hit P. I hit negative P. I found my way home. I left enough breadcrumbs. And what's the shape of the curve between those 2 points? Given by the load. The load is 0. What kind of curve has 0 slope? Horizontal line. There is your shear diagram. If I would have done this with the function method, I'd have had to written 1, 2, 3 sets of equations. See how much work I did here besides applying the principles? I don't hardly have anything written down. That's where you're going to go. Cool. Does everybody do that? Cool. Nice. You may not think that now, but it's really cool. By the way, the Germans did this too in like the 1860s and 70s. Everything we know about structural mechanics today, the Germans did it in the 1860s and 70s. They were well ahead of their time. Cool. All right. So now what do we do? Well, we're done. It seems to work. So now I'm going to come in and say, well, since I have my shear diagram, I'm now going to use my shear diagram to construct my moment diagram. So I'm going to say positive X, positive moment, and my units will be kip feet. Do I know the moment somewhere? What is the moment at the beginning of my beam? 0. What is the moment at the end of my beam? 0. So again, I know where I am. I know where I want to go. I just need to connect the dots. So how do I connect the dots? Do I just close my eyes and scribble any line in there I want? Well, you're welcome to do that. But that would probably not be very useful for you in passing the test. So let's apply what? Our basic principles, which say now the change in moment is the area under the shear diagram. All right, so what would be the change in the moment from 0 to L? Well, at 0, the moment is 0. So what's going to be the moment at L? It should be the area under the shear diagram. What is the area under the shear diagram? It's a rectangle. Base, which is L, times height, which is P, PL. And by the way, that's a positive area. So I should get a positive change. So I should hit PL. The differential part of this relationship says that the slope of the moment diagram should be equal to the shear. So let's go up and look at the slope. So the slope starts at a positive value equal to P, and does it change? No, it's constant. What kind of curve has a constant slope? A straight line. And what would be the slope? Positive P. This is a slope of positive P. In fact, if you wanted to come in here and measure it, it would be P to 1. So that's how the moment changes under this portion of the curve. Now let's go to the next section. The change in moment is the area of the shear diagram. So from L to 2L, what's the area of the shear diagram? 0. No change. So if I start at PL, I stay PL. What's the slope of the moment diagram? It's the value of the shear. What's the value of the shear here? 0, and it stays 0. What kind of curve has a 0 slope? Horizontal line. From 2L to L, what's the change in moment? Well, we hope it hits back here to 0. So what kind of change would I need to go from this point to this point?
Negative change.
A negative change in how much?
PL.
PL. So let's see, is the area under the shear diagram equal to that? Well, let's go up. The area, it's a rectangle. Okay, cool. Base L times height minus P. So the change is minus PL. So I do go from here to there. Great. I found my way home. Now, how do I get there? Well, according to this, the slope of the moment diagram is equal to the shear. So starting here, the shear starts off at what kind of slope? Minus P. Does it change?
No.
No. Constant slope, straight line, negative slope, down. In fact, if I check that, that would be minus P to 1 for slope. So there is my moment diagram for this problem. What's the maximum moment in the beam? Where does it occur? Between L and 2L. Does that look familiar to you guys? Think way, 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 way back to the spring of the freshman class you took. Does it now look familiar? If you took that class. That was the way we loaded our reinforced concrete beams. And where was the maximum moment? In the middle. Where was the shear zone that you had to concern yourself with? The ends. We didn't have to worry about shear in the middle because there was no shear. See how easy this is? Any questions about this one? We're going to work a lot more, so if you're not really finding...
right?
No. It's a starter problem. Okay.